Cisco Certified Network Associate Day 36. Welcome back everyone. I'm Imran Rafai, your trainer for this entire series. Today we're going to learn spanning tree protocol. This is a topic a lot of people get scared. This is one of the most difficult topics, and it is difficult because people don't really understand what it does. I hope at the end of this video and maybe the next video you would understand how spanning tree works, and you're gonna be so comfortable talking and dealing with STP. So without wasting much time, let's get straight into today's class. And before we go ahead, this is my beautiful Windows desktop screen for this week. To know how to make your screen look like this, click on the link on the top right hand corner of the screen right now. And like always, before we go ahead, please click that subscribe button right below this video and also that bell icon so that it notifies you whenever we put a new video. And no, don't forget to click on that like button, which is your way of saying thank you. And as always, on the left side my company contacts, on the right side my personal contacts. And for everyone who keeps asking me what is my email address, it is imran.rafai@nwking.org. And like I have mentioned in my previous videos, the best way to contact me is by commenting on this video on YouTube. If not me, one of my staff or your fellow learners would be able to help you, and that'll be the quickest way. You could email me, but like I said, because of the number of emails that I get, I may not be able to reply to all of you. I do reply to some of you, but if you don't get an email back from me, please don't feel disheartened. It's just that I'm not able to give enough time for everyone. But yes, one way you could get a reply from me is by donating and being one of our donors. And of course, my donors, I really love my donors. You are the reason why we have such wonderful contents coming for free. So people who can't afford, that's fine, you can watch, enjoy, but people who can afford, please consider donating, and the donation links are there on our website, right? So without wasting much time, let's go to our class today. Today, like I said, we are following the ICND exam topics as per Cisco's website, and today we are following 1.3, and 1.3 is configure, verify, troubleshoot STP protocols. 1.3a, it says STP mode, PVST plus and RPVST plus, and then STP root bridge selection. Because the topic is quite big, I'm going to take up this in the next video, that is day 37, and I think I'm going to add this as well to day 37. So what are we going to look at today? We're going to look at what STP is. We'll try to understand STP. We'll look at STP modes, that is PVST plus and RPVST plus, and then we will look at bridge ID and port cost. These are some of the components to understand bridge election process. The bridge election process, like I said, we'll be looking at next video. So we will look at the bridge ID and port cost in this video, and then we'll be ready for the root bridge election process in the next video, right? So we need to understand what L2, layer 2 loop is, right? We discussed this in one of our videos earlier in this series. So if you watched from the beginning, I'm sure you would have been introduced to STP a while ago. But to summarize what STP means is, if let's say we have two switches, and let's call this switch A, and then we have switch B. If I have two links to the switch, right, and if there is a broadcast, let's say for instance there is one user, let's call her Joe, and then we have another user, Jim, right? But if Joe sends a message to Jim, Joe sends that frame onto switch A. Now switch A does not know the MAC address for Jim, so what it does is it would send a broadcast. Now if he sends a broadcast, or if switch A sends a broadcast, that broadcast goes out on all the interfaces. Like if that message comes from here, switch A would say, okay, fine, I can see that it's coming from here, so I'm going to send that broadcast out on both the interface because I don't know where that MAC address is. Now when this MAC address, when this broadcast comes to B, switch B, by definition of broadcast, it means that if you are in the same broadcast domain, you collect that broadcast in one of the interface, send it out in all the other interfaces. So switch B would take that message and send it to Jim, and also this message coming from here would be sent back on that interface, and message coming from there would be sent back on this interface, right? So this broadcast would come back to switch A, and switch A would do the same thing. Switch A would think this is a new broadcast, it'll take that and put it on this interface, and the broadcast coming from here, it would take and put it on that interface. So this will go around and around and around. This becomes a loop, right? It goes in loops, and let's say by that time there is another broadcast coming on that interface, right? And that also will go through the same process of loop. They would take from one interface, put on the other interface, put on the other interface. So this is a layer 2 loop, and layer 2 loop, when it happens this way, it creates a broadcast storm, right? Basically, so many broadcasts come onto that network that that whole network is unusable. So this broadcast storm can only be stopped if one of the devices fail or one of the links fail. So in such that the loop is broken, right? If one of the links fail, then of course there is no loop and all the broadcast dies out there. If let's say physically one of the links don't go down, one of the switches will fail, because after some times, if the broadcast storm becomes so strong, one of the switches will run out of its memory and it will fail, and it'll restart again, and the broadcast storm gets sorted out. But that's one of the problems. The second problem is MAC address instability, right? So this is switch A and this is switch B. Let's in this case put another scenario, and ideally in today's world, this is more than having two links between switches. This could be one of the reasons why you have a loop. Again, you have 3 devices, and 3 devices still form a loop around. So if one device sends a broadcast for whatever reason, and this is F0/1, and this is F0/2, and this is F0/3. Now when this user sends a broadcast to switch A, and let's take another color, and let's assume this user has a computer with a MAC address of AAA, right? Like some AAA something. Switch A, whenever a frame comes in on F01, it says the source MAC address is going to be this, and it is destined to go to, let's say, the other user here, and that got a MAC address of BBB. So it says source MAC address is AAA, sending to destination MAC address of BBB. Now switch A says, okay, I see that your source MAC address of AAA. That means now AAA is available on F0/1. That is for sure. It doesn't know where BBB is. That is another problem to solve, but it definitely knows where AAA is. So it updates its MAC address table and it puts that information there. Now since it doesn't know BBB, it says I'm going to broadcast it. I'm going to flood this onto all my available interfaces. So he sends that message onto both his interface, F0/2 and F0/3. Now let's assume switch B, since it's connected to this MAC address of BBB, when switch B receives this message, it says fine, I know where BBB is. I'm going to put this, and of course let's say this is, okay, I'm gonna use black. Okay, so this is again F0/1, F0/2, F0/3, right? So when switch B receives this broadcast, it says I see that you're coming from a source MAC address of AAA. So switch B also says, okay, I can see AAA is connected to, it's or reachable through my F0/2 interface. Fine. And I know, let's say it already knows that BBB is connected to its F0/1, so it sends that message to BBB. Now if you remember previously, A had sent that same broadcast to C as well, so C would forward that broadcast. Now C would be coming in, this broadcast would be coming in from F0/3. So when B receives that broadcast, it says, okay, you're saying that this is a message coming from a source MAC address of AAA, but I know that AAA is connected to my F0/2 earlier. Now for some reason I need to update this, so it updates as AAA to F0/3, right? So it says now AAA is available on F0/3, right? So because of the, now when this broadcast again starts going out here, switch A also would start getting confused, because switch A originally thought AAA source MAC address was connected to F01, but then now this broadcast would tell it's connected to F0/2. Similarly, this would also go out on this interface, and when this reaches here, now switch A would be confused, because now F0/3 also says that AAA is connected to them. So constantly the MAC address table would be updated between these three interfaces, and that creates a problem. So that is the MAC address table instability problem. So first we had the broadcast storm problem, and then we have the MAC address table instability, where every few seconds the MAC address table had to be updated because of a layer 2 loop. That's the second problem. Now third problem is, if you remember here, this user sent a message or a frame or packet to switch A. Switch A sent it out on both its interfaces, right? So when switch B received it, switch B forwarded that to the correct user, which is BBB. That was the destination. That's fine. So this user received the frame, but because switch A had also sent that same frame to switch C, now switch C will also forward that to switch B, and switch B will say, okay, you want to go to MAC address of BBB, so I'm going to send it. So this user would get the same packet twice, right? That's a problem, because if it's an application that was sending the data, the same frame cannot come twice. If the same frame comes twice, there's a duplicate frame, and there is some problem in the network. So multiple copies of the same frame is reached to the user. So these are the three problems a layer 2 loop can create. Now the solution to all the problems that we discussed in layer 2 loop is a protocol called STP, Spanning Tree Protocol. Now if you watched my previous video where we discussed STP many videos ago, I don't even remember the video number, I think it's day 10 or day 12, I don't know. Anyway, one of the videos where we discuss port modes and things like that is a way where you break the loop in the network. So typically in today's world, like I said, loops happen when there are devices connected and it forms a loop, a broadcast loop. So if these are all in the same broadcast domain, they're all switches, and there is a loop that is formed. STP protocol, using this STP algorithms, we'll discuss about algorithms and how it works. It decides one of the switches to be a root switch. Okay, so let's make switch A as the root switch. Now it says every port connected to the root switch has to be in the forwarding state. So this port and this port will be in forwarding state, right? So it will be forwarding packets and frames to the root switch. So whatever is connected to root switch directly, that has to always be in the forwarding state. Now from this link between B and C, one of the ports in fact will be in a state called as a blocking state. That means it will not be able to forward traffic. Physically they would still be connected. That means B can still send traffic to C. It's just that the port in C, it will not process. So switch C will not process traffic received from switch B, right? But physically they're still working. So how does it work? It works using something called as BID. BID is bridge ID. Now you need to remember that STP protocol was invented and written way before the Ethernet switches were invented, right? So since the protocol was invented or written before the Ethernet switches were invented, you would still find the term bridge used many times, and most of the terminologies in STP still works in a bridge concept. I mean, concept wise it's exactly the same. There's no problem between switch and bridge. It's just that the term bridge is still used. So bridge ID is what it is used, even though it should be switch ID, it's still called the bridge ID. the messages that these switches exchange to understand and to do an election, to find out who the root switch is, and to keep updating each other, is something called as BPDU, that is Bridge Protocol Data Unit, BPDU. Again, you see bridge, it says bridge, but that's all it is, so don't get confused. Even though it says bridge, it still refers to switch, right? So these BPDU messages, they keep exchanging every 2 seconds. That's the hello timer. It has a hello timer of 2 seconds, so every 2 seconds it keeps updating each other. And what do they update? They update first, they update about the root switch MAC address and BID of the root switch, and it tells what is the cost for it to reach the root switch. And now, what is cost? Each port has a cost depending on the speed. We'll talk about it in, I think, the next slide or the slide after that, so don't worry about that. So this is how they break. So they ultimately try to break. Logically, they shut down one of the ports, or they put that port in a blocking state, and that breaks the loop. So now broadcast sending out, let's say if C sends a broadcast, that will go to switch A would forward that to switch B would forward that back to switch C, but switch C's interface, since it's in blocking state, will not process that, and hence the loop is broken, right? That's what basically STP is. Now STP is IEEE 802.1d standard. It's a very old standard, so it is open source. It is IEEE standard. The problem with IEEE 802.1d or the common STP is it takes about 50 seconds, right? It takes 50 seconds to go. If let's say there's some change, one of the links breaks, for it to update, it takes a maximum of 50 seconds. That is, it has 2 seconds of hello timer. Then it has, so basically what happens is it has states blocking state, then it has 2 intermediate state called as listening state and learning state, and then it goes to forwarding states. Now hello messages comes every 2 seconds. So every 2 seconds these devices exchange hello messages. So C will send hello to B, C will send to A will send to B. Each of them updates BPDU hello messages every 2 seconds. If at all any device does not receive a hello message, it waits for 10 times the hello timer, right? So by default it is 2 seconds hello timer. That means it waits for 20 seconds or 10 hellos, right? If it misses 10 hellos, then it starts updating, it starts taking action. Now start taking action is, it goes to the listening stage and it stays there for 15 seconds, and then it goes to the learning states and it stays there for 15 seconds. So totally 15, 15 and 20, it's 50 seconds, right? So it takes a lot of time to converge, and in a switching world that is a lot of time. To improve on that, IEEE wrote another standard. I think it is in 2004 it came out with another standard called as 802.1w, which is nothing but rapid spanning tree, RSTP. Now RSTP improved upon this timing. They first thing, RSTP does not have the 2 intermediate states. It directly goes from blocking to forward, or forwarding to blocking. In both the ways it would go instantaneously, whereas in STP, blocking to forward, it took a lot of time, but if a port had to go from forward to blocking, that was instantaneous, right? But in RSTP, blocking port is also called as discarding state, not port, discarding state. The blocking state is called as a discarding state in RSTP, and then there were no intermediate state. Directly it goes to the forwarding state. From blocking state to forwarding state, it would directly go in. Also, the forwarding state had something called as the alternate port. In STP there used to be a root port, right? Root port are the ports that it connects. So in this case, this is a root port, RP, and this port is a root port, right? In RSTP, these root ports, other than having a root port, it would also have an alternative port, right? So in this case, this would be an alt port and this would be an alt port, right? So it has configured an alternate port. So in case the root port breaks, or that link breaks, the alternative port automatically quickly, instantaneously becomes the root port. So in this case, if this breaks for some reason, automatically the alt port would come up and this would become the root port, right? Instantaneously. Even worst case scenario, it would take 10 seconds to converge. In this case, it would be 50 seconds. So it is 10 seconds versus 50 seconds. So basically, that's the difference between STP and RSTP. RSTP, it is a slightly faster, not slightly, it's much more quicker than STP. And as more and more technology came, RSTP was something that IEEE had to come out with, right? So it's called Rapid Spanning Tree Protocol. Now, Cisco implemented STP in a slightly different way. The problem with STP is STP considered the broadcast domain as one single domain, and it worked in the native VLAN or the default VLAN. So VLAN 1 is where STP considered. So it considered all the traffic to be part of that one large broadcast domain. That didn't really work, especially with newer devices. And Cisco has been implementing VLAN for a very, very long time. So Cisco said, you know, we're going to implement STP in slightly different way, called as the PVSTP, right? That is per VLAN STP. So the same thing, it said every VLAN would have an STP, which the IEEE 802.1d couldn't do, right? They couldn't do. So they had to do it in one default VLAN. They did it in the VLAN 1, but Cisco came up with PVSTP, where each VLAN had an STP running. So each VLAN could have a different root bridge, and they could have the same STP process in each VLAN. And when Cisco upgraded, or when IEEE upgraded to Rapid STP, Cisco also went to something called as the RPVSTP, right? So the only problem was the Cisco's PVSTP and RPVSTP had to run the ISL, the interswitch link encapsulation, and you know this is a Cisco proprietary encapsulation. And the IEEE 802.1d and W, RSTP and STP, worked on 802.1q encapsulation, right? Cisco said fine when ISL was having its limitations, and Cisco said, you know, maybe we should go to 802.1q encapsulation. Cisco improved on their PVSTP and RPVSTP by supporting 802.1q, and that is what our PVSTP plus and RPVSTP plus, right? So RPVSTP, PVSTP is per VLAN STP plus, and RPVSTP is rapid PVSTP plus, right? So it's exactly the same thing. It's just that it now supported ISL and 802.1q, and now this is the industry standard, PVSTP and RPVSTP, right? So in the STP process, we discussed port cost. Now port cost, earlier there were port speeds. We had ports that had 10 Mbps, 100 Mbps, 1 gigabit Ethernets, and 10 Gbps, right? So when they assigned cost, they assigned 100 for 10 Mbps, then 19 for 100 Mbps, 4 for 1 Gbps, and 2 for 10 Gbps. There were no costs for 100 Gbps and 1 Tbps. So in 2004, IEEE said the new standard costs were 2,200,000, 20,000, 2,220 for these port speeds. Now these port speeds are good, so you can understand, and becomes easy. You know, as the speed increases, the cost decreases. So if you have two links, we had a fast Ethernet link and a gigabit Ethernet link, you know the gigabit Ethernet link would have much lesser cost than the fast Ethernet, and hence if when the election process happens, the gigabit Ethernet port would get preference, right? So always the lesser cost will have preference. You will see that. I think most probably you will see that in the next video, because we would look at the election process in the next video. But just understand, this is how costs are calculated. Next, we're going to look at the bridge ID. We spoke about the bridge ID. Now in STP, bridge ID had 2 bytes of data. So this is 2 bytes. Each block is a byte. So this is 1 byte, this is 1 byte. So the bridge priority had 2 bytes of data, and the MAC address was 6 bytes of data, right? So every switch has a MAC address. So that MAC address plus a priority together forms the bridge ID. That is STP. Now PVSTP plus improved on this. So this STP had 2 bytes of data, that is 16 bits. PVSTP, that is Cisco implementation, they said the first 12 bits would be part of something called the extended system ID. That is nothing but VLAN numbers. So if VLAN was 1, so this has 12 bits. 12 bits would give you 4095, 0 to 4095, and if you know, our VLAN numbers would, with extended VLAN, goes from 0 to 4095, right? So whatever the VLAN number, that would be represented in the first 12 bits, rightmost, and the leftmost 4 bits would represent the bridge priority. Now if you know binary arithmetic, and if you look at our magic table, these 4 has a place value of 4096, 8192, 16384 and 32768, right? So that has 16 combinations. Each of these, it could be all 000, so that becomes priority becomes 0, or it could be 0001, that is 0 0 0 and 1, and if you add the place value, that's 4096, so that would have a priority of 4096. Or depending on any of these bits, if you change the bits, it would all be one of these numbers. So you have these 16 combinations, and if you look at it, each of them have an increment of 4096. So by default, all Cisco switches have a priority of 32768, but you could choose any of these numbers as a priority, right? These are the only valid numbers that you can use for your bridge priority. Now, so when you're working on Cisco switches, you always have to remember that 32768 is by default the priority, plus you will add the extended system, right? So this will be 32768, and then if you're working on VLAN 1, it will be 1, so 32768 plus 1, 32769 would be the bridge priority for VLAN 1, right? So VLAN 1's bridge ID priority would be 32769, and you would have the MAC address, right? If you remember, I said for the bridge ID, it is bridge priority. This whole thing becomes a bridge priority, that is 32769 plus the MAC address of whatever that is, right? So if the MAC address is AAA, this becomes the MAC address. If there is another device that will, let's say if it starts 32769 and if the MAC address is BBB, if you compare this, the priority is matching, so that's a tie-in priority. It then looks at the MAC address and you see that this device got a lower MAC address and this device has more priority, right? And in the election process, this priority plays a very, very big role. So just understand this concept. You know, if you want to watch this video again, just watch it, but you need to understand how the bridge ID works, right? If you want this device, even though this MAC address is more, we cannot change the MAC address part, but we definitely can change this part. So you can go into the switch and change it to any of these numbers. So if you want this device to have more priority, you could give it 0. You could give the bridge priority part to be 0. So 0 plus 1 for VLAN, so it will be 0 plus 1, so the priority will be 1, and then the MAC address, and this will always have more priority on any of these devices with a higher priority number, right? So this is how the priority works. So you need to understand that, so just watch this video again. And like always, today's offer is day 36-50 off, that you would get a 50% off if you want to purchase anything from our website, and that's how you can support us. So please go ahead, feel free to purchase something from our website. So thank you so much. Like I said, this is a very, very important topic, so I would request all of you to watch this video once again, and it is always going to help you, right? So thank you so much for watching, and see you back very, very soon for the next part in this series.